Welcome to the class again. So today we are going to learn about the signed and unsigned numbers representation. In the previous lecture we were doing some digital arithmetic operation. We did the basic addition, multiplication and subtraction. For the most part in this course we will actually be doing addition, so our more focus would be on that. And in the previous lecture we were also just focusing on the unsigned numbers, which are basically the positive numbers, adding positive numbers with positive numbers. Today we are going to do a bunch of examples. I'm going to go through some of the techniques that you could use to represent a unsigned number, signed numbers and unsigned numbers, including the signed magnitude representation, the 1s complement, and also the 2s complement. 2s complement is one of the most popular technique that is used to represent the signed number in digital systems, and we're going to focus more on that, and you'll see there are a couple of advantages of that over the other techniques. Okay, so let's get started on this. Again, those of you who came late, there's some supporting material at the back, please pick it up. Unsigned binary numbers, these are the positive numbers. Okay, by definition positive numbers and thus do not require an arithmetic sign. For n-bit unsigned number represent all numbers in the range. What is that range? We have done it Tuesday and also on Thursday. Yes. 2 to the power n minus 1. That is correct. Okay. So for example, the range of 8-bit unsigned binary number is going to be 0 to 127. Correct? Okay. How about 16-bit? That is going to be from 0 to 65,536. Okay. So for 16-bit, you put n equals 16, and for an 8-bit system, you put 8 in that equation, and that should help you find out the range. And this is for the unsigned binary number. This is what we have done so far. For the signed numbers, which are the negative numbers, it's a little different. Okay. Signed numbers, on the other hand, are negative numbers that require an arithmetic sign. The most significant bit of a binary number is used to represent the signed bit. If the signed bit is equals to 0, the signed binary number is positive. However, if it's 1, that binary number is considered negative. The remaining bits represents the actual number. Okay, so one thing to remember here, when we are looking at the signed bit, which is actually your most significant bit, if it is 0, that means it's a positive number. Okay, if it's 1, that means it is a negative number. Okay, alright, so here is an example. You have a 8-bit binary number 0011010. This word here, so different system would have different size. For example, if you have a memory size of 8-bit, then a word is 8-bit. If you have a 16-bit machine, that is a 16-bit word. So here's an 8-bit word, and because the most significant bit is 0, that means it's a positive number, and rest of the bits are going to just magnitude of that number. So the weight for this bit is 1, is 2, 4, 16, and 32. And if I add these, you basically get 53, right? And because 0 is a signed bit, which means a positive number, so this is going to be a positive 53, okay? Say I want to represent negative 53 in an 8-bit binary system. What would be the code then? Come on, quick. Yes. Correct. So the most significant bit is going to be 1, which will represent this is a negative number, and the magnitude is going to remain same, which is 0, 1, 1, 0, 1, 0, 1. Okay. This represents negative 53. Okay. All right. An n-bit signed number represent all numbers in the range. Again, like I mentioned earlier, there are 3 different ways of representing signed number. We're going to focus on 2s complement. For 2s complement, to find the range, here is the equation. Negative 2 power n to 2 to the power n minus 1 minus 1. Okay. So for example, the range of a 3-bit signed binary number is going to be what? Negative 2, 3 minus 1, 2, 2, 3 minus 1, minus 1, and that gives you a range of negative 4 to positive 3, right? Similarly, for an 8-bit signed binary number system, the range is going to be negative 128 to positive 127. Again, just plugging this value for n over here in this equation and then finding the range. This will be important, and I'll mention that when we go to the example later on in the lecture. Okay, all right. So 3 ways to represent negative numbers. Number 1 is a sign magnitude representation. How we use that? Well, most significant bit in a binary number is going to represent the sign. Okay, remember, what is a sign? If it's 0, it's a positive number. If it's 1, it's a negative number. Please let me know if I get out of focus, okay, or you can't see the bottom part. All right. And the remaining n minus 1 bits are preserved and represents the magnitude of the number. Okay, so here we have a 4-bit binary system. You're going to treat the positive numbers just like you do. So 4-bit binary system, most significant bit for a positive number is going to be 0, correct? And what is the 3-bit code for 3? It's 0, 1, 1, right? So here's your 4-bit system right here, correct? This is positive 3 in a sign magnitude representation in a 4-bit system. If it's a 5-bit system, how would the code look like for positive 3? It's going to be 000 11. Okay, so you have to make sure this is the key word here. 4-bit binary code for positive 3 is different than for a 5-bit binary system. Okay, so what is going to be the code, 4-bit code for positive 7? The most significant bit is going to be 0, and then 3-digit code for 7 is 111, right? And similarly 0, 0, 0, 0. Okay, what about negative 3? What is going to be the sign bit here? 1. Okay, and then the 3-bit code for 3 is 111 or 011. What about negative 7? Sign bit 1, and then 111, and 0 minus 0. One of the reasons we don't use sign magnitude representation is because it has 2 representation for 0. One is positive and one is negative. And you see the code it generated is 2 different ones. 0000 and then 1000, which could be confusing to the digital system and also for us. So that is one of the reasons we don't use this method. There's one small example right here below. Similarly, sign magnitude representation of negative 15 as an 8-bit binary number will be what? Again, the sign bit is going to be 1. Okay. What is the 7-bit code for 15? Quick. Yes. Correct. 000 1 1 1. Okay. If you remember 15, we did it yesterday. It was 1111. That's what you get. We have 8-bit system, so rest of the bits are going to be 0, and most significant bit is 1 because this is a negative number. So this corresponds to negative 15. Okay. All right. Let's move to the next page. We're moving on to 1s complement representation. Here, most significant bit also represents the sign, which again 0 is positive and 1 is negative. The remaining bits are inverted for negative numbers only, not for the positive. So the positive numbers are pretty much similar to what we had for the sign magnitude. Positive numbers are represented in the same way as in the sign magnitude method. Okay, so you have 5, right? Negative 5. What is the code for 5? It's 101, right? And say this is a 4-bit system, so the signed bit is going to be 1, okay? And what would you do to the rest of the bits here? Because it's a negative number, the remaining bits are inverted for the negative number. Because it's a negative number, the remaining bits are going to be inverted. So what is the invert of this 101? It's going to be 0, 1, 0. So in 1s complement representation, -5 is 1, 0, 1, 0 in a 4-bit system. And again, it may change in 5-bit or 6-bit. Okay, so don't get confused why we are getting two different binary codes for the same number in different configurations. We'll try to finish this table here, right here. For example, 1s complement representation illustration in a 4-bit binary system. +3, this is going to be what? 0, 0, 1, 1, right? 0, 1, 1, and then 0, you got 0, 0, 0. Okay. -3, guys. Signed bit is going to be 1, and then you're going to invert the remaining bits, which are correct. So 3 is 0, 0, 0, 1, 1. You invert that, you get 1, 0, 0, and that's what I have here, 1, 0, 0. Okay. Similarly for 7, it's 0, 1, 1. You invert it, and you get 1, 0, 0, right? Yeah. Okay. All right. So what is going to be the signed bit here? 1, and rest of the bits are going to be 0, 0, 0. And what about here? Signed bit is going to be 1, and the rest of the bits are going to be 1, all ones, right? Okay, all right. Here's the big one. 1s complement representation of -15 is a 8-bit binary number, will be. Signed bit is going to be 1. 7-bit code for 8 is 000 1 000. Oh, it's a 15, right? 15, yeah. Okay. 4 ones here. Okay. So 1 and rest of the bits are going to be inverted. So you got 111. And then these bits are going to be inverted to 0. Okay. So this is your binary code for a signed number, -15, and 1s complement representation. Okay. Is that clear what we have covered so far? Simple, right? Okay. All right. We are moving to 2s complement. Please give your fullest concentration here. In my experience, most students have difficult time understanding this part, this technique. Okay. Okay. All right. Now, 2's complement of a signed binary number. Bits are inverted for negative numbers only, and then 1 is added. Positive numbers are represented in the same way as in the other two methods. So positive number is same for all 3 techniques that we have done so far. We'll be on the third one. Negative numbers, each technique has a different way of doing it. For this technique, what are the steps involved for a negative number? Well, convert the decimal number to its binary form first. Second step is to take the complement of it, meaning convert all the zeros to ones and ones to zeros, and then add 1 to complement using the regular binary addition. So we'll do examples here. Okay, let's start with this. What about +3? Again, it's a 4-bit binary system. So the code will be 0011, right? Okay, 0111. And then this is going to be 0, 0, 0, 0. Okay. -3. What is the first step? What is the first step for taking the 2s complement? Yes. Binary. Okay. All right. So this is what is the 4-bit code for 3? 0011. Correct. What's the next step? Inverted, right? So this becomes 1 1 0 0. What's the next step? Add 1. If I add 1 to 1 1 0 1 or 1 1 0 0, what would that be? It would be 1 1 0 1, right? Say if I write it this way, 1 1 0 0, and I add 1 to it, what do I get? I get 1 0 1 1, right? Okay, so this is what? This is the 2's complement of negative 3. So I'll write it down over here. 1 1 0 1. Okay, all right. How would you do it for 7? What is the 4-bit binary code for 7? 0 1 1. Okay, so the next step is to invert the bits. So we get 1 0 0, and then next step is to add 1. So I add 1, and I get what? 1 0 0 1. Correct? So this will be 1 0 0 1. Okay. What about 0, negative 0? What would be the code for that? Anybody tell me real quick? So what is the 4-bit code again? 0 0 0 0. Invert the bits, you get 1 1 1, right? And you add 1 to it then. So what do you get? 0 0. 1 plus 1 sum is 0, carry is 1. 1 plus 1 sum is 0, carry is 1. What happened when we were taking the 2's complement of the 0 in a 4-bit system, it actually generated a 5-bit number, right? So this 5th bit on the leftmost side, we're just going to discard it. So it comes out to be 0 0 0 0. So notice in a 2's complement system, this 0 and this 0 are same, right? So this gives us a huge advantage, and it just eliminates the risk of creating any confusion among the users and programmers, and also among in the digital systems. Okay, all right. So the major advantage of the 2's complement, perhaps, is its simple implementation at the logic level design, and we'll do more of these examples. Microcomputers therefore use 2's complement to represent n-bit signed binary numbers in the range negative to the power n minus 1 to positive to the power n minus 1 minus 1. It's the same equation from the previous page. Okay, all right. So the range of the 8-bit signed binary number is going to be what here? This range is going to be what for 8-bit system? Come on, guys. Minus 128 to positive 127. When I say range, what it means is in an 8-bit binary system, you can actually represent numbers from negative 128 to positive 127. Say I want to represent negative 129. I cannot do it in an 8 binary system. I'm going to have to increase my number of bits. Okay, so say if I am using a 9-bit system, that expands my range. Okay, all right. So we will move on to the next example that we have here. So we got 20 in decimal, and then we have negative 16 in decimal. The code for 20 is right here. Again, just to verify, 1, 2, 4, and 16. So 16 plus 4, 20 here, and this is 16. Because 16 is this is negative 16, so we're gonna have to do that process again. What's the first step? We get the binary already. Next step is to invert, right? So 1 1 1 0 1 1 1 1. Okay. All right, next step is to add 1. Okay, so I add 1 here. Okay, 1 plus 1 sum is going to be 0. 1 plus 1 sum is going to be 0. Carry is going to be 1. 1 plus 1 sum is going to be 0. Carry is going to be 1. 1 plus 1 sum is going to be 0. Carry is going to be 1. 1 plus 1 sum is 0. Carry is going to be 1. This 1 comes out as it is. And then they have this 1, 1, and 1. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So this is actually my negative 16 right here. Okay, 20 was this right here. So I'll just write down here 000 1 0 1 00 1 2 3 4 5 6 7 8, and then this right here 0 0 0 0. Okay, and we are going to add these, right? Correct, because this is already in negative, right? Okay, 0 plus 0 gets you 0. 0 plus 0 gets you 0. 1 plus 0 gets you 1. 0 plus 0 is 0. 1 plus 1 sum is 0. Carry is 1. 1 plus 1 sum is 0. Carry is 1. 1 plus 1 sum is 0. Carry is 1. And 1 plus 1 sum is 0. Carry is 1. Okay. Now notice here, again we added two 8-bit numbers and we got a 9-bit number. So what are we going to do with this leftmost bit right here? Say again? Yeah. So this is what we refer as a carry out bit. Okay. And we just simply ignore it. Okay. Ignore it or discard it. Okay. This right here is your most significant bit, also which is your signed bit, and because it's 0, which means this is a positive number. Now if we look at the magnitude or weight of individual bits, 1 2 4, this actually makes what number? 4, right? And because this was 0, so this is a positive number. And if we do the math here, 20 minus 16 gives you 4. Okay, so we just proved that, right? Also, because it was a negative, it was an 8-bit, and the range for the 8-bit was that we calculated in the previous on the previous page for an 8-bit system was negative 128 to positive 127. Because this 4 was in this range, we were able to do this operation. If you are doing addition or subtraction, but the number is not within the range, you might get a data, but it will be a false data. There will be an error in there. Okay, so that's why knowing how many bits you have and what you could do in that given range is important. Okay, that condition we call it as an overflow. Okay, and I'll explain that later. Okay, let's look at some of the ranges. Unsigned was pretty simple, right? This will be 0 to 7 right here. 4-bit went from 0 to 15. And 8-bit was 0 to 255, right? Just plugging in these values right here in this equation. Okay. For 2's complement, this is going to be minus 4 to positive 3. 4-bit, putting 4 here, this is going to be negative 8 to positive 7. Okay. Here, this is going to be negative 128 to positive 127. Okay, it's good to know these ranges. Okay. Okay, so I was earlier talking about the overflow. Let's explore what that is. Okay, I'm just going to pick this 3-bit. Okay, 2 is complement. Three-bit. So if we look at the range, it goes from -4, -3, -2, -1, 0, 1, 2, and then goes, actually, yeah, and then goes to 3, right? Yeah. Okay. Now, here we have negative numbers and we have positive numbers. When you add a negative number and a positive number, the answer you get, does that exist in this range? Say you pick -4 and +3. When you do the math on a -4 plus 3, what do you get? -1, right? Is -1 in that range? That means there is no overflow. Okay, so this is kind of a law and rule, and just remember that whenever you are adding one positive number and a negative number, there will never be an overflow. You can try any combination. You can try -3 plus 0, you still get -3, right? Which is still in the range. But say if you are adding 2 plus 3, then you get 5, right? And 5, because it's not in there in the range, it's going to throw false data. Okay, that means there's an overflow. Okay, so you will have overflow when the result is out of the range. Okay, so this is important. Okay, any questions so far what we have done? Is everybody following it? Okay, great. Fantastic. Let's move on to our next example. Okay, here's a little bit more definition of it. Overflow occurs when the answer to an addition or subtraction problem exceeds the magnitude, which can be represented with the allotted number of bits. Okay, right. -3 plus 2, and we would know should get -1. This is the answer what we are looking for. Okay, it's a 4-bit system. Okay, so again, because this is -3 here, and 3 is equivalent to 0011, that's the 4-bit code for it. We have to convert, take a 2's complement of it, right? So the first step includes inversion. And the second step would include add 1. So 1, 1, 0, 0, plus 1. 1 plus 0 gets you 1, 0, 1, and 1. Right? Okay. So 1, 1, 0, 1. That's -3. What is going to be the code for 2? Come on, guys. Yes. 0010. Okay. We don't give any special treatment to any unsigned number, positive number. Okay. Positive numbers are pretty much going to be the same. If you remember, we did this table. So all the unsigned numbers are going to be same. So 0 is 000 in a 4-bit system. 1 is 0001. We don't give any special treatment to the unsigned numbers. Okay. All right. So we add these, and this is +2, get -1. Okay, 1 plus 0 is 1, 0 plus 1 is 1, 1, and 1. Okay, what happens here? The most significant bit is what? It's 1 means what? It's a negative number. Okay. How do we represent a negative number in decimal? What were the steps? We're going to have to do these steps again, right? Because it's a negative number right, in a 2's complement. So I'm going to write it down here. This number goes here, taking 2's complement. Okay, what's the first step? Invert 0, 0, 0, 0. Second step is add 1. 0 plus 1 is 1, and then 0. 0, 0, 0, 1 represents what code, in what number in decimal? 1. And because the number was negative, so you add a negative sign to it. Okay, is that what we were expecting? Yes, we were. Okay, 3 minus 3 plus 2 gives you negative 1. And because negative 1 is within the range right here, there was no overflow. Okay, so one of the problem on the homework might ask you do the math and say if it's a positive number or a negative number, or whether there's a flow or not, overflow or not. Here there's no overflow. Okay, okay, all right. I'll also just write down the range over here for a 4-bit, because this is 4-bit. What was the range here? Negative 8 to positive 7, right? Okay, 5 plus 6 is going to give us 11. And we know already that 11 is not in the range, so there is going to be an overflow. But doesn't mean that you should not do this part. You're still going to do it, but there's a way before you even start working on this, you would know there's an overflow or not. Okay, all right. So this is 4-digit code for 5, binary code. 0101, and then 0110 is for 6. So this is 5. This is 6. All right, 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is, sum is 0, carry is 1. And then 1 plus, this comes out 1. Okay. And again, the most significant bit, the sign bit is, it's a negative number. Okay. So what do we do with a negative number? We take a 2's complement, right? 1, 0, 1, 1. We take invert those bits, and then we add 1. So 0, 1, 0, 0. Adding 1. You get 1 here. 0, 1, 0. This corresponds to what number in decimal? 101. Come on, guys. 5. Okay. And because the sign bit was negative, so this is a negative 5 in decimal. That is what 2's complement binary system telling us. Whereas the answer should have been 11, right? Okay. So we say there's an overflow here. Okay. Let's do one more example. This is negative 4 plus negative 5. Again, we're expecting negative 9 here. Okay. 4 is 0, 1, 0, 0. Invert it. Add 1. Okay, so 1, 0, 1, 1, and adding 1. 1 plus 1 is 0, carry is 1. 1 plus 1 is 0, carry is 1. You get 1 and 1. Okay, this is negative 4. and then we have -5, which is 0, 1, 0, 1. You invert that, you get 1, 0, 1, 0. You add 1 to this, get 1, 1, 0, 1. So this is your -5. Okay, all right. Let's put those numbers right here. -4 is 1, 1, 0, 0. And then 1, 0, 1, 1 here. This is your -5. Okay, all right. We add these. 1 plus 0 is 1. 0, 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 1, 0. Okay, all right. We added two 4-bit numbers, and we got 5-bit number. What are we going to do with the leftmost bit? What do we refer this bit to? Get rid of it. This is a carryout bit, and we just ignore it. Am I the only one who's feeling hot? Okay. Okay, carryout bit, and then we just ignore it. Okay, all right, and this is our signed bit. So it looks like it's a positive number, right? So do we need to take a complement to his complement? No. So this would mean what? +7, whereas we were expecting -9. So what was the reason we didn't get the right answer? Because there's an overflow here, right? -9 is not in the range right here, okay? Just narrowly misses. Okay, overflow. Okay, all right. Moving on to our next example. Okay, so solution to overflow. How can we avoid that situation? Well, earlier we were discussing if there's a way for us to increase the number of bits, we can increase our range, right? So adding a bit can expand the range. Okay, and how we do that? For the positive numbers, we are actually going to add 0 to the left. And for the negative numbers, we are going to adding 1 to the left. Okay, when I say to the left, means to the left of the signed bit, right? Okay, all right. So now we are adding a bit, so it's a 5-bit system, correct? Now this is a 5-bit system. Okay, so the 5-bit code for 5 is 00101, and 00110 is for 6. Okay, let's add this. 1 plus 0 is 1, 0 plus 1 is 1, 1 is, sum is 0, carry is 1, and then this is 1 and this is 0. Because the most significant bit is 0, so it's a positive number. And let's look at the individual weight of these bits. 1, 2, 4, 8. And when we add these, we get what? 8 plus 2, 10. 10 plus 1 is 11. 0 positive value. Okay, so we were able to avoid the overflow this time, whereas we could not do it with a 4-bit system. Let's do another example. It's actually the same example. -4 plus, by the way, what is going to be the range for a 5-bit system? Yes. Anybody? Yes. Negative 16 to positive 15. Okay. Okay. All right. We know we are expecting negative 9 here. Now, again, it's a 5-bit system. Okay, this is interesting how we do it. Okay, we are 5th bit, which is the most significant bit on the left hand side, is going to be the sign bit, right? Remember we said for the negative numbers we are going to add 1 to the left. Okay, so let's just forget about that. What is the 4-bit code for 4? It's 0100, right? Correct? Okay, all right. We will do the 2's complement here first. So invert it. So you get 1 0 1 1 and then add 1. Okay, so you get what here? 1 plus 1 is 0. 1 plus 1 is 0. You get 1 and 1, right? Now we add 1 to the left. And why we do add 1 to the left? Because it's a negative, right? Okay, all right. Similarly, same thing we do for the negative 5. So 5 in decimal is 4-bit code is 0 1 0 1. Take invert of that number 1 0 1 0. Add 1. One plus 0 is 1. 1 0 1. And what do I add to the left? 1, right? Okay, all right. I'm going to put these numbers right here on the side. 111, 100, 1 2 3 4 5 bits, and then double ones 1 0 1 1. Okay. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0. Carries 1. And this comes out 1 1. Okay. Now, again, we have a situation here. This is our what? Okay. This is our carry out bit, right? We ignore it. Okay, and this right here is your sign bit, right? And because it's 1, so it's a negative number. Okay, and what do we do with the negative number? We take a 2's complement of it, right? Okay. All right, so we are taking 2's complement here. First step is invert, so 0 1 0 0 0. If I add 1 here, what would this number be? Come on guys, 0 1. Correct. Okay, this makes a decimal code of 9, right? 1 2 4 8. 8 plus 1 is 9, and because this was a negative number, you get a negative sign here, and that's what we were expecting here, right? Okay. All right. Let's move on to the last example. We got roughly 5 more minutes. Okay. All right. Okay, negative 78 plus negative 35. Okay, I went ahead and got the binary codes for 78 and 35. These are the 8-bit codes. So what are we going to do here? 2's complement again, because both are negative, right? So invert the bits 1 0 1 1 0 0 0 1, and then add 1. So you get 1 here. 1 plus 1 is 0. Carry is 1. 1, 0, 0, 1, 1, 0, 1. 2, 3, 4, 5, 6, 7, 8. Right? So this is your negative 78. We do the same thing for 35. Let's invert the bits. 1, 1, 0, 1, 1, 1, 0, 0. Add 1. So you get 1 here, 0 here, triple 1, 0, 1, 1. Okay. And this corresponds to negative 35. Okay. Remember, we're just doing this 2's complement here. Okay, all right. I'm going to put these numbers here. Okay, 1, 0, 1, 1, 0, 0, 1, 0, and then negative 35, double 1, 0, triple 1, 0, 1. And then we are adding it. Okay. What do we get? 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 sum is 0. Carry is 1. 1 plus 1 sum is 0. Carry is 1. 1 plus 1 sum is 0. Carry is 1. And then 1 plus 1 plus 1 gives you 1, 1. Okay. Okay, all right. What do we do with this bit right here? Ignore it. Okay. What is this bit right here? This is the sign bit, and it's a negative number. Okay, so therefore, which would mean we're going to have to take the 2's complement again. So let me rewrite that number. 1, 0, 0, 1, 1, 1. Okay, all right. Inverting it first. 0, 1, 1, 0, 0, 0, 0, and then adding 1. So you get 1, 0, 0, 1, 1, 1, 0. Okay, all right. Let's add these numbers 1, 2, 4, 8, 16, 32, and 64. Okay, what do we get here? 64 plus 32 plus 16 plus 1. 113. And because this number was negative, so it's negative 13. And if you do the math here, negative 78 minus 35, this gives you negative 113 as well, right? So with this, we finished our tutorial. That's perfect timing, right? It's 12:49. Enjoy your weekend, and I'll see you guys on Monday, okay?